My name is Marwa Al-Salami. In this video, I'll be explaining the solution for assignment 2 on graph-based path planning. I'll be looking at two key algorithms, the Grassfire algorithm and Dijestra's algorithm. I'll go over how each one works, their advantages and limitations, and why Dijestra's algorithm provides the optimal solution for this problem. Let's get started. First, let's talk about the Grassfire algorithm. This algorithm is a type of breadth first search that expands outward from the starting point in a wave-like patterns until it reaches the goal. It assigns a step count to each node based on how many moves it takes to reach them, but it doesn't take edges weights into account. This means it assumes all paths have equal costs, which is not the case in real-world navigation. Now, applying Grassfire to our problem, we get two possible paths. The first one would be from the starting point over here to E, from E to R, from R to F, and from F to the goal, which is the cost of 15. In the second path, from the starting point to D, from D to E, from E to R, from R to F, and from F to the goal, which is the cost of 11. Well, the issue here is that the algorithm selects the path based only on steps taken, not on actual travel costs. That's why it's not the best approach for this scenario. Now let's move on Dijestra's algorithm, which is specifically designed for weighted graphs. This algorithm finds the shortest path by considering the actual distance between nodes. It does this by keeping track of the minimum cumulative cost to reach each node. The steps of Dijestra's algorithm in our graph are as follows. We start at the start node with the cost of 0 mile and update its neighbor. Distance to D equals to 3 miles. Distance to E equals 9 miles. Distance to B equals 1 miles. We pick the closest node, which is B, equals to 1 mile, but it doesn't provide any better path, so we continue. Next, we have D, which equals to 3 mile, and it's processed, and it updates E to 5 miles, a shorter path than before. Following this, E updates R with 7, and R updates F to 9 miles, and F updates goal to 11 miles, which we have it over here. The final shortest path found by Dijestra's algorithm is start to D node to E, from E to R, from R to F, from F to the goal, with a total cost of 11 miles. This proves that considering weight leads to a much more efficient path selection compared to Grassfire. Now let's compare both algorithms. The Grassfire algorithm is simple and useful in grade-based environment, but it doesn't work well for graphs with varying edges costs. It identifies the shortest path in terms of the number of moves, but not in terms of actual travel distance. This makes it unusable for problems where distance between nodes vary significantly. Dijestra's algorithm, on the other hand, is a cost-sensitive search algorithm that guarantees the shortest path based on real distance. It ensures that we always select the most efficient route by prioritizing the lowest cumulative travel cost. And that's all for my solution. Thank you for watching.